Okay, and we are go. That was just a short quiz covering what we did last time. Solving systems. Hopefully by this point you're sort of becoming experts on solving systems. Yeah, the answers for that quiz, they're already up on the website, so you can check those as soon as you leave. And we will be continuing with 1.2. We'll finish it now, and then go on to chapter 2. So I showed you a couple, well, I told you about the 3 cases for solutions, right? For any linear systems, what are the 3 situations for solutions?
No solution, many solutions, and who wants to?
No solution what?
Many solutions and one.
What is many?
Infinity.
Infinitely many, right? You can't have a finite number of solutions other than one, right? You have either have one unique solution, infinitely many solutions, or none at all. Those are the only 3 possibilities. Okay, so I did an example when we had one unique solution. I did an example when we had no solution. It was inconsistent. Let's show you what infinitely many solutions look like and how you deal with it. And that was actually the bonus problem on your quiz. So let's see what something like that looks like. There's a system that will have infinitely many solutions. Augmented matrix, what does it look like here? 1 minus 2, 3. Minus 2, this part is okay. 1 minus 2, 3. 2 minus 1, 3 minus 7. Okay. I'll skip the details because I really can't bother with that. Basically, the reducer or echelon form of this guy would actually end up looking like this. Try this at home. Might end up with something like a row of zeros. Okay. So that will end up being the reducer or echelon form here. Now if you look at something like this and you want to start writing down solutions. What is x1? What is x2? What is x3? You'll start to notice something, right? These 2 here will give me equations like this one, the leading variable would be x1, right? This one would give me an equation where the leading variable is x2. I can solve for that guy. But then this guy, what do I do with it, right? So this process here is simple. Okay. See which columns, at least I think I'm going to write down a summary of the steps afterwards, so I don't have to write it down now. I'll just explain now and I'll write down all the steps later. When this happens, you're going to identify your pivots, right? I have a pivot here, a pivot here. The important thing is what columns these pivots fall into, right? Remember, each column corresponds to a certain variable, right? So the first column is the x1 variable, this is x1. The second column is the x2 variable, this would be the x3 variable, right? So now, basically, you notice that in the x1 column, there's a pivot. In the x2 column, there's also a pivot. In the x3 column, no pivots, right? What that means is that this guy can essentially be anything. You can't really solve for him. You can't say he's this number, right? So what we do when that happens, you get to a situation like this. You identify where all your pivots are. Any column that does not have a pivot, you set that variable equal to a parameter. Right? So this was here, x3, I'm just going to call it t, right? Where t can vary, can be any number. So I set it to be whatever guy, he can be anything. And then I start to solve for the other guys in terms of this guy. So in row 2, what does row 2 tell me? x2 minus x3 equals minus 1. Now remember my x3 is actually t. So I can plug that t in here, and then I can solve for x2. x2 is minus 1 plus t. or t minus 1, and count t. And then go back to row 1. Now in row 1 we have x1 plus x3 equals minus 4. And so I can solve for x1, that's minus 4 minus t, because my x3 was t. This leads us to this sort of solution. x1, x2, x3 equals, you start out by writing it as a column vector as usual, right? So your x1, you write what your x1 is, which in this case is minus 4 minus t. Your x2 goes here, which is minus 1 plus t. Your x3 is just t. Any questions so far? No? We're okay? Okay. So now, the reasons why we'll do this will become more clear later, but for now what you want to do is you want to write this as, you see me, I said in the quiz, write as a linear combination of column vectors. The idea is you want to separate the different kinds of vectors. You want to separate the different kinds of parameters, right? And this exercise will be much more important when we go back, start talking about vector fields. But for now, that's what we're going to do. Notice that here, I have constants that are not attached to any variables, and I also have one variable, the t. What I want to do is I want to separate these two, right? Separate the constants and separate the parameters. So in this vector, what would be the elements?
Minus 4 minus 1, 0.
Right? I'm just looking at the constants. Here there's a 0 plus t. Right? So I'm going to take all the constants, make them into their own vector. Then I'm going to take all the t's, make them into their vector. So I can factor the t out because it's a scalar. I can factor it out based on the matrix operations. And what would be here?
Minus 1, 1, 1,
Minus
1.
Minus 1, 1, 1. Does this remind you of anything?
The part that's augmented.
The last one, last column. No, sorry.
Reminds you of Calc 3. What from Calc 3? Well, parametric equation would look like this. X equals that, y equals that, z equals that. What is this?
Is that like a normal check?
What kind of curve is it? What?
Plane.
No, it's a line.
A line.
Yes, you have to remember what these things look like. It's a linear system, right? Which means the only other things that will ever happen would be linear. So it's going to be like a point, a line, a plane, or an n-dimensional plane, right? This happens to be a line that passes through this point with this direction vector. It's saying that when I intersect these three planes, they actually intersect in a line. So it could be something like that, right? Where all these three planes, they intersect in a line, which passes through a point, minus 4, minus 1, 0, and it has the direction vector, minus 1, 1, 1. Right? So that's sort of the geometry that's happening here. We can have three planes. If they intersect in another plane, well, here we have infinitely many solutions as well. Notice that this is infinitely many solutions. Because here, every single point along this line will be a different solution. Every t value I pick will give me another point on this line, and they will all solve this system. So that's the geometry of what's going on here. And one thing you can notice, the most these three planes can ever intersect with is in another plane, right? You'll find that the solution set to a system of equations, the highest dimension the answer could be in is the dimensions defined by the variables. And we'll talk about dimension a lot more when we get to vector spaces. But for now, I just want to show you that sort of the geometric picture. Right? So whenever you have like a row of zeros or something like this, what happens is you just look for a situation where not all columns will have a leading 1. Whenever that happens, you let the guys without leading 1s be a parameter, right? They can essentially be anything. The guys with leading 1s, you can solve for them in equations in terms of the other guys. If we look at, let's just do it. Any questions on this so far? What we did? So, for example, if I look at quiz 4A, just picking a random one, I'm looking at the bonus now. So I had x1 plus x2 plus x3 plus x4 equals 2, x1 plus x3 minus x4 equals minus 1. The augmented matrix for this would be 1, 1, 1, 1, 2, and 1, 0, 1, minus 1, minus 1. Version B was very similar to this. But you had that, and what were you supposed to do? What would we do in the next step?
Take negative rho 1 plus rho 2.
Right, I can take this minus that, right? So I can say 1 minus 1 is 0, 1 minus this is 1, minus that is 0, 1 minus this would be 2, 2 minus this would be 3. This is rho 1 minus rho 2, and I would have probably flipped rho 2 to be clear. So now what you've noticed, this is the x1 column, the x2 column, the x3 column, the x4 column, right? Where are the pivots? Here and here, right? x1 and x2 have pivots. x3 and x4 do not, right? So what do we do for x3 and x4? Turn them into parameters. Of course, you use two different variables. So here you set x3 equals, I think in the solutions I use k, but it doesn't matter what you call them, just as long as you know that there are other parameters. S is a very typical parameter to use, but if you're writing it by hand, people always mix it up with a 5. So I don't like using S when I'm writing by hand, but like in the book, they might use S and T a lot. So I just let x3 be k, x4 be t, and so now I can start with row 2. Remember, we always go from the bottom row up. Row 2 is going to tell us what?
x2 is equal to
x2
3
plus
minus
x4.
3 minus 2 t.
Right, plus 2, let's write it. 2x4 is equal to 3. Now x4 I know is t, so I can bring this to the other side. So my x2 is equal to 3 minus 2t. In row 1, I would have x1 plus x3 minus x4 equals minus 1. Now I know that this guy is a k, and I know that this guy is a t. So when I bring this over, I have minus k. Bring this over, I have plus t. And so now I can write out my solutions. x1, x2, x3, x4. x1 is this guy. x2 is this guy. x3 is a k. x4 is a t. And I want to write this as a linear combination of column vectors, where I'm separating them by the parameters. So here,
Negative 1, 3, 0, 0. Negative 1, 0, 1, 0.
these are just the coefficients of the variables. Hopefully you're seeing that. And this would be
1, negative 2, 0, 1.
now, the kind of surface that's spanned by two vectors is just a plane, in the sense that you know from Calc 3, right? So it turns out that the solution to this, I have two 4-dimensional planes intersecting in a 3-dimensional plane. Right? Because these are the two vectors that span the plane, and it contains this point. Right? So here's my plane, there's the point minus 1, 3, 0, 0, and then there are two vectors spanning that in the plane, which happen to be these guys. Minus 1, 0, 1, 0. and 1 minus 2, 0, 1. So that's kind of the picture. So we can't draw the 4-dimensional planes for you, but this is the solution to those 4-dimensional planes. Every point in this plane is a solution to the intersection of those two. Right? And that's where these parameters come in handy. They're actually talking about direction because they can vary. You're varying the points, and you're varying them in 2 directions. So that means you get a 2-dimensional surface as the solution. So just want to show you that. That was the trick when you have infinitely many solutions. So let me just summarize this. Yes?
If you're given a curve and you have to find a system of linear equations, how will you go?
You can't.
You can't?
You're right. Not in general, no.
Not in general.
Yeah. So these are just linear equations. What you could do sometimes with curves is, let's say I had 2x squared plus 3y squared equals 5, and then x squared plus 3y squared equals 2. Something like that I could think of as linear equations because I just can replace x squared with a single variable, solve them with a linear system, and just know that whatever I get, I'm going to take the radical of it, right? But if something like that happens, all bets are off, right? So it's a very specific kind of situation.
What if you're not given equations but only points and then a graph? But it's not a linear equation. It's
Oh,
not
yeah, you can find the coefficients that way, yeah. We actually did that in a homework problem last time, I think, where we were like, there was a parabola, they gave us a parabola that passed through 3 points. You could actually solve for the coefficients that way.
What if it's not a parabola?
Anything, you could do anything. By plugging in the point, then your variables aren't variables anymore, they become numbers. Right? So let's say I had something like y is equal to ax cubed plus bx squared plus cx plus d, and I know some points that this passes through, right? I can literally plug them in for x, in which case it's not a variable cubed anymore. My variables would be the a, b, c, which are linear. They don't have any powers. I could solve for the coefficients.
Oh, okay.
So, but for the variables themselves, setting up a system where the variables themselves are not linear, using a linear system, most cases it won't work. Before I do the summary, there's one kind of system I want to talk about in general. So, recall we can express a linear system as ax equals b, right? Where a is the coefficient matrix, x is the solution matrix, right? So whenever they're asking you to find the solution, they're telling you to find x, right? And this is b. There's one particular kind of equation that's going to be really important to us, and we'll come back to it later a lot. If b is actually a 0 vector, then the system is called a homogeneous system. These guys are insanely useful, and we'll use them a lot when we get to vector spaces. But whenever you have all zeros in your answer column, we call that a homogeneous system. Some facts for now. Do you think we can find solutions to a homogeneous system? What would be a solution to a homogeneous system?
The origin.
The origin. If x itself is a 0 vector, then I multiply by anything, I'll get a 0 vector, right? So homogeneous systems are always consistent. they will always have at least one solution, right? Namely the zero vector. So the zero vector will always be a solution to a homogeneous system, because if you plug in all your variables equals 0, you're going to get 0, right? So that's one thing that you need to know about them. So a homogeneous system will always have either one solution or infinitely many. It will never be the case that this guy will have no solution. When the only solution is this solution, something magical happens, which we'll talk about later. Right now, because this is sort of the solution you don't have to think about. Mathematicians use a word to describe it that they use to describe everything you don't have to think about. Trivial. X equals 0 is called the trivial solution. Anything else I want to tell you about this? The system may have non-trivial solutions, right? Solutions that are non-zero. In which case, it will have infinitely many. So, thought I'd mention homogeneous systems. Like I said, it's a very important kind of system, and we will be using it all the time when we get to vector spaces. It can give us a lot of information about the system and what a system is describing. So that's just some facts for you there. Now I can talk about the summary. I'm going to talk about in general how to solve a linear system. One, write the augmented matrix. Two, put the augmented matrix in row echelon form or reduced row echelon form. Of course, you can use your personal preference unless required otherwise. Generally, it won't matter. The only reason I ask you on quizzes to do reducer echelon form is it's easier to grade because there's a theorem that says the reducer echelon form of any augmented matrix is unique, right? So I can know that you're doing everything right and you have the answer. But an augmented matrix can have several reduced row echelon forms, right? So this is not unique, but that one is, so it's easier to spot it. But other than that, there really is no difference. Well, they'll give you the same answer when you try to use them to solve a system. So if solving a system is the goal, it really doesn't matter which one you choose, unless I specifically say do this one. In which case, I'd usually ask for the reduced or echelon form. 3. Identify the pivots. Or identify the columns without pivots. Or maybe I should talk about consistent versus inconsistent first. check for consistency. E. If there is a row 0, 0, dot, 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 A, where A is non-zero, no solution. Otherwise, we go on to step 4. Identify the columns with no pivots. Set the corresponding variables. Equal to parameters. So identify the columns that don't have pivots, corresponding variables, set them equal to parameters, and you write your answer as a linear combination of column vectors. So I can say linear combination here, or I can say a sum of column vectors. 5. If every column has a leading one, then we're back in the simple case that we did last time. Then you can read off your solutions directly. And again, another useful fact. Whether you're in reduced row echelon form or just row echelon form, the same columns that don't have pivots will not have pivots, either form you're in. Right? So they both bring you to a very efficient point. You can identify readily from either row echelon form or reduced row echelon form who has pivots and who doesn't. And one who doesn't have a pivot, they're a parameter. If everyone has a pivot, then you just read off the numbers. And of course, in this case, you have a unique solution. Just mention that, I guess. In this case, once you have parameters involved, it means you have infinitely many solutions. So you augment it, reduce it, check for consistency. If something like this happens, it's inconsistent, no solutions, you stop, right? If nothing like this happens, then you have two situations. You will either have a unique solution or infinitely many. You can identify which situation you have based on how many leading ones there are, right? If you have a leading one for every column, you have a unique solution. You can just read off the answers. If you don't have a leading one for every column, that means some guys are parameters, you'll end up with infinitely many solutions. You can have solutions up to as many dimensions as there are variables. So if I have like x, y, z, to be consistent, I can either be a point, in which case I have a unique solution, or I can be a line, in which case I have infinitely many, or I can be a plane, in which case I have infinitely many, right? I can never be a four-dimensional solution to something that only has 3 variables, right? You have to be at that dimension or lower to be a solution. So, which is another way from geometry where you can tell why there can be only one versus infinitely many. Because going from one dimension to the other, you're adding an infinite number of things anyway, right? To go from a point to a line, you're adding an infinite number of points. There is no in between. You can't take 5 points and make a line, right? So you can't get a finite number of solutions other than one. So that's just summarizing what we did. I guess there are no questions on that. I talked about homogeneous solutions. So I think I mentioned this in an email to you guys, but I think I'm going to do things a little bit different from the syllabus. So this completes 1.2. So the homework for that is due next class. But I don't want to move on to 1.4, which is the next section. I actually want to start with 2.1. We're going to talk about determinants. For a book organized this way, to me it makes sense to talk about determinants before they talk about inverses, because you actually use a determinant to find an inverse. So it's kind of, to me it was like putting the cart before the horse. So at one point, it's like in section 1.4, they're like, okay, here's the formula for a 2x2 determinant. By the way, here's the formula for the inverse of a 2x2 matrix. By the way, this part here is called a determinant, but we don't know what that is yet. Just trust us on this. It's fine. Maybe move on. I didn't particularly like that. It's like someone telling me, just put this in your food, right? You'll gain a lot of muscle, and then 2 weeks later we'll do that. Wait, what? Come again? What is this in my food? Don't worry about it. Just trust me. I'll tell you later. No, you want me to ingest this thing that I don't even know what it is? No way. No, tell me what I'm putting in my food first. So I'm going to talk about determinants. Okay. There are a lot of things I want to say about determinants. I probably won't say everything, but I will say some things. Because usually in a course like this, people just say, okay, this is how you find a determinant. But I was never satisfied with that when I was in linear algebra, so I guess I'd sort of tell you what determinants are, what they mean. So I sort of want to go there. So, but first let's do a familiar formula. Let A be a 2x2 matrix. Let's say I have A, B, C, D. Then the determinant of A is given by, it's called DETA, or you might use the notation, the size of A, even though it's not technically a norm or an absolute value. It's that's the notation for it. So for a 2x2 matrix, what's the formula? AD minus BC, right? You do this X thing, and then you multiply it. So AD minus BC, right? So they tell you that, okay, that's how you find a 2x2. Now they go on to 3x3 and 4x4, but then I'm like, what does that mean? What is this? What is that number? Why is it that crisscrossing actually gives me that? And why is this meaningful? Why is it so useful? What the heck is that? Right? So I thought I'd tell you guys a couple things. Okay. Let's sort of explain what this guy is, and then we can go on to determinants. Where does this AD minus BC come from? Let's look at one thing. Consider one interpretation, consider this. I'm considering a system that has coefficient matrix A, right? AX plus BY, CX plus DY, EF. Now pretend this was the days before we learned about augmented matrices, and let's say we just want to solve this, right? One thing we could do is try to do the elimination method. That's one way. So what I could do is, for example, I could multiply the top by D, so row 1 times D, and I can multiply the bottom one by minus B. This should be a Y minus BF. Now what do you notice happens? The Y's have the same coefficient. And so I eliminate these guys. I would have ADX minus BCX is equal to DE minus BF. Now I can factor out the x and divide by that guy, provided it's not 0, of course. DE minus BF over, AD minus BC. Interesting. Okay, what if I wanted to solve for y? I could do a similar thing, right? So if I had ax plus by equals e, and I have cx plus dy equals f. Let's say I want to solve for y. I'm going to try the same thing. Do these guys here. So let's say minus c minus bcy minus ce. Take equation 1 times minus c, and then bcx plus and I'm multiplying this by a, so a dy equals af. Multiply this by a. Now I can add those two. The x's actually cancel this time. I end up with a dy minus bcy equals af minus ce, and I can solve for y. And there's that guy again. Right? Now there are a couple things I can take from this. One, notice that this system cannot have a solution if that formula is 0, right? You can't divide by 0. So somehow this expression is very intimately acquainted with a system of equations given by this coefficient matrix, in the sense that I can tell you when it will have a solution versus when it doesn't. By the way, this is another way for Kramer's rule, for those of you guys that don't know. This is actually the 2x2 determinant of when you replace this. But we'll talk about Kramer's rule later, actually. Right? So this expression is not some random expression that you get with an x. It actually sort of means something. There's something deeper happening here. But I find it's kind of weird to talk about something in terms of its usefulness in solving random equations, because matrices don't only represent equations, they can represent other things. Yes?
Why did we choose to multiply the first equation by d?
Doesn't matter what. No matter what I did to work that out, I could get to that point. You always have that formula for x. So then I'm like, okay, maybe there's something more concrete here. Of course there is. Let's not talk about solving equations. Let's talk about something deeper. What does it mean, this determinant guy? Sort of like in the sense of, like with integrals and derivatives from calculus, right? You sort of had a geometric feel to what those guys were, right? Like the integral was area, right? You draw a curve, look at the area under the curve, that's the integral. It's something like you can see. There's a picture that goes with it. right? The tangent line, the slope of that line that you can draw, you can see it right there, that's the derivative, right? So is there such an interpretation for the determinant, something that's more concrete, say geometrically? Turns out there is. So let's look at it another way. So consider this guy. As two row vectors stitched together. It doesn't make sense, it doesn't make a difference whether you think of it as column vectors or row vectors, but I want to draw a parallel with something else from Calc 3. So we're going to go with row vectors stitched together. Right. So there I have two vectors, A, B, and C, D. Now these can look any way. It depends on the values of A and whether they're positive or negative. But let's say for argument's sake, because I want to illustrate this, that I could actually draw these guys. I'm pretending all the coefficients are positive and they line up in this way, but it doesn't matter how you think of it actually. Just want it to look nice so you can see where things are coming from. So say I draw the vector AB, position vector, boom. That's AB, right? So this is a vector that hits the point A comma B. And I go boom. This is the vector that hits the point C comma D, right? Create a parallelogram with them, right? That's going to be the area where you find this resultant vector of the two vectors, right? Now this point here is going to end up being what point?
Isn't it addition of the two?
You have to add the two vectors to get that point, right? So you add the two x coordinates and you get A plus C. Add the two y coordinates, get B plus D, right? Now let's say I ask you, what is the area of this parallelogram? And like ask you, figure out the area of a parallelogram. Okay, so we could do some sort of Calc 3, take a projection down here of this and get the height. No, not that. We don't want to get too complicated. Here's an idea. Create a larger shape. Right? So you see all this shaded region here? I don't want it, but I'm going to create it because it's convenient to look at. Right? Now clearly the area of this parallelogram is going to be the area of the whole rectangle minus the shaded area. Right? Why did I do the shaded area? Well, I can cut this up into shapes that I know, right? Like this is a rectangle. These would be two right triangles, right? And I can find the areas of those guys. So here, area of parallelogram equal to area of large rectangle minus area of the shaded region. Now let's actually look at what this would actually be. What's the area of the large rectangle? What's the height here?
2A plus
It's just length times
B
width,
plus
right?
D is the height.
So it's A plus C times B plus D, right? So this is equal to A plus C times B plus D. Minus, I'm going to want to take all these shaded regions with you. Now you can actually use the coordinates here to figure out that it's actually symmetric, right? What I get from one side, I'm going to be the other side. So let me just focus on this shaded area, and then I'm going to double what I'm taking away. Okay, so let's look at this rectangle here. What's the length, what's the dimensions of that rectangle? The height is B, okay, the base? C, right? Because this whole thing is A plus C. I know that this is A because that's the x-coordinate of this vector, so that must be C. So then this guy is actually going to be the same as that guy. So BC, right? There are two of them, two BCs. Now let's look at this right triangle here, right? What's the area of that guy? Half the base times the height, right? The base is C. What's the height?
D.
D. Right, so I can say 1/2 CD. Right, that's C and that's D, right? Okay. Now what about this triangle? Half the base times the height. The base is, and the height is, so it's 1/2 AD. Right? You good so far? Let's simplify some stuff. Multiply it. What do I get? AB plus AD plus BC plus CD minus 2BC minus CD minus AB. Start to simplify. CD minus CD, AB minus AB. I have BC minus 2BC, that leaves me with a minus BC, and an AD. There's that expression again. It turns out that's what a determinant is. In a very concrete geometrical way, it's the area of a parallelogram. Which parallelogram? The parallelogram spanned by the row vectors of whatever matrix you're looking at. Now it turns out the vectors didn't have to look this way. They could be going over here, all over the place. So it's somehow, just like how with integrals you can get negative area, with here you can get the negative area of the parallelogram. So that's actually what a determinant is. Right? And also, in Calc 3, you actually had a point where there was a part in chapter 10, I forgot what section it was in your textbook, where you had three vectors, vector A, A1, A2, A3, vector B, B1, B2, B3, vector C, C1, C2, C3. And then you created a three-dimensional parallelogram with these guys. Remember that? We called it a parallelepiped. Right. This was a three-dimensional parallelogram. Does anyone remember the form for the area of a parallelepiped, the volume of a parallelepiped? In Calc 3, this was called the scalar triple product. It was equal to the absolute value of what we call the scalar triple product. The formula for the scalar triple product was A dot product with B cross C. And when you actually worked out what that was, it turns out it would look like this. A1, A2, A3, B1, B2, B3, C1, C2, C3. Now what you'll notice this guy is, it's actually the determinant of a 3x3 matrix. Right? In other words, to find the area of a two-dimensional parallelogram, use AD minus BC. To find the volume of a three-dimensional parallelogram, use the determinant of the 3x3 matrix, which had its own formula. You did that whole thing with the cross product, you know, that plus, minus, I. And that was actually how you found the volume. Now, back in Calc 3, you probably didn't appreciate this is what you were doing, but that's what you were doing. You were actually finding what we call a determinant. And the reason you were finding it was to find a volume. Right? It was linear algebra happening all around you. You didn't even realize it. Okay, so let's go back to the determinant. What is the determinant? Now, you remember how when you were doing this, there was something minus something, and there were plus minuses, the blah, blah, blah. What was happening with that is, what you were really doing was you were creating a bigger box around this guy, finding the whole area and then subtracting off the empty spaces. That's why you had these plus minus signs alternating. That was what's really going on. You're just adding up volumes and then subtracting the volumes you don't need. It's a wavy definition, but this is sort of how you can think about it in many cases, which later when I tell you about some theorems with the determinant, you'll start to see, yeah, it actually makes sense that that would be the case if I think of determinant as a volume. So one way we can talk about, let A, B, and n by n, it has to be a square matrix. The determinant of A denoted det A, or put the matrix in absolute values, is defined as a function I call it the det function. It goes from the set of n by m matrices to the set F. Right, this is the set of n by n matrices. Set of n by n matrices. To either a real or a complex number, such that for any input, the output is the signed volume of the n-dimensional parallelogram. Of the row. You could actually get the same thing using column vectors. You could even try it at home. If you think of it as column vectors, you would have gotten the same thing. Column vectors. The inputs. In other words, the determinant of A, i.e., is equal to the plus or minus the volume of the n parallelogram spanned by A. This is what a determinant is. So later on, I'm going to be telling you some theorems about, oh, if you have a matrix and you multiply a row by a constant, you have to multiply the determinant by that constant. The reason why was, well, if you have a box, right, and you double one side, you'd actually double the volume, right? You triple one side, you triple the volume, and so on and so forth. But each dimension of that box corresponds to a row in a matrix. So it means if you multiply a row in a matrix by a number, you actually change the volume by that same factor, right? So there are things like that that we're going to be telling you later, like, oh yeah, in the determinant, you multiply this by that, this is what happens. And the reason why is because it's a volume. You're actually manipulating a volume. If you switch two rows, it's like you're flipping into another axis, and then you can turn a determinant into a negative volume. So that's why if you have a matrix, you find its determinant. If you switch two rows, you actually take the negative of what the answer would have been. It's because you're like taking this volume and flipping it in another axis, right? When you switch two rows, you're switching the order of the vectors, so they go in opposite directions. right? So there are a lot of things that come out of determinants that really come from this idea of it being a volume. And it leads to a lot of intuition that could be helpful. And it's just something nice to know where it comes from. Next time we're going to be doing Laplacian. I think like by the next class, we should finish everything we can want to talk about with determinants, I guess. Should be a problem. So we'll stop there. 1.2 is due next class. And yeah, that's it. We'll continue with determinants. I'll tell you how to find them specifically for any size square meter.